So this is a question and answer session on timber design, in particular timber beams. All right, where do you guys want to start?
I'd say with K9, that was the first thing we were struggling with. So say,
All right,
I'll give
let
you
me
an
do a
example.
quick overview of the other things on our way. So I'm going to share this screen. Can you guys see that?
Yep.
All right, so the capacity of a timber beam. There's a mistake here already. I can see there should be a phi right there. Phi MD is the capacity of the timber beam. There's the phi value, which is pretty straightforward. The K1 value is about the duration of the load. How long is it loaded for? You guys understand all that? So permanent loads, it's 0.57. Yep. For short-term loads, it's 1, depending how short-term it is. K4, does anyone remember what that's about?
That's the moisture content if you're talking about seasoned or unseasoned timber.
Thank you. Yes. So if you have timber that gets drier, you get a slightly different value of K4. K6, I think, is about temperature. Yep. Basically, if you're a Queenslander, you use a lower value than the rest of us. Well, it's a bit far north in Queensland, in the tropics, let's say that. All right, K9. We want to start on K9?
Yeah, that's on with the All
right. K9 is talking about where you got lots of beams working together. If you look in Yassine's background there, you can see there's a bunch of timber beams above his head, right? Basically, this is saying, as long as you got a decently strong floor connecting those timber beams, if one of them is a bit under strength, it's made up for by the fact that the ones around them are probably a bit over strength. So it's allowing a bit of load sharing that way. Because timber, as you appreciate, is a natural material. So we've got quite a range. In any one class of timber, we've got quite a range of materials from quite strong to quite weak. Okay. And so we pick a strength, which is the 95th percentile. So if we say it's going to be, 17 megapascals, 95% of it's quite a lot stronger than that. 5% is weaker. And we got these safety factors and stuff to, like, what are we going to do about the 5%? And this is saying that in a system like above Yassine's head there, if one of those is a bit weaker than the others, it's going to be made up for the fact that the others are stronger. So that you've got, they have to be joined by something which is capable of taking a bit of load out of the side. So for a single beam, which is, we've got one beam, if it's weak, there's no load sharing. Or if there's no system in place that can share load from one beam to the other if it's a bit weak, then K9 is 1. That's your simple case, okay? But then we've got two situations. One is sometimes you've got beams and they're actually directly nailed together. Okay, they're right next to each other, they're connected together, they're working together. With them, there's always a lot of load sharing. The other way is, like above Yassine's head there, you've got beams with spaces in between them. And the G factors are all about that spacing. So I'm going to have to try and open the standard, which is a bit awkward in my screen, but we'll see how we go here. That's probably too small to read, isn't it, guys?
Yeah,
I'm going to do this.
Struggling a bit, sorry.
Yeah, that's all right. I'll do this a bit differently. I'll share the screen a bit differently, but let me just find the space first. Where are we? K9. All right, let me find K9. Shear strength. We are in beams. So I don't have the printed version of the standard with me today, so I'm looking up one on my computer, which is a bit more awkward. Oh yeah. Okay, let's stop this share. If you guys can open up that PDF document I had open and have it beside you.
Yep.
All right, and now you guys can hopefully see a, you can see the beam, sorry, the standard there.
Yep.
Actually, let me try one more method. Does that make it any clearer if it's like that?
Yeah, that's good for me. Thank you.
Good. Okay. All right, so there's our equation. MD equals phi K1, K4, K6, K9, K12. K9, the modification factors given in section 2. So we've got to go back up to section 2. That is the thing about the timber code. You've got to flick from one, bit to the other. Here are factors here for K9. All right. This is the bit on K9 here. Strength sharing structural systems. Okay. In determining the K factor, K9 for a discrete parallel system, the effective number of elements should be taken as N-com times N-nem. All right. N-nem, M-com is the number of elements that are effectively fastened together to form a single group, and N-nem are the number of members that are discretely spaced parallel to each other. So, for example, in the system above your scene's head there, the N-com is 1 because each of those members are separate.
Oh, yeah.
In this example on page 25, the N-com is 4 because you've got 4 beams nailed or bolted together. Okay? So this K9 factor handles both of these things at the same time. All right, and if you look in this factor here, the second one, combined parallel system where you got the 4 beams with S between them, that's effectively the system above your scene's head. All right, N-com is 1 because they're all separate, and N-nem is 4. So N-com times N-nem is 4, and we've got a G32. I'll come to the G31 and the G32 factors in just a second. Finally, if you've got a combination of them, they're in groups of 3 nailed together and they're spaced out like that. Not very common, but it does happen. Then you come down to this equation. Where's our G31? Table 2.7. Table 2.6. Table 2.7. Here we go. Here is our G31 and our G32 factors. So let's do Yassine's example above his head there, right? Our N-com is 1 because they're all single beams. So our G31 is 1. All right. What this is saying is if you've got 2 beams nailed together, you get to increase their strength by 14% because you've got this averaging effect. All right. And our N total number of members in a parallel system, you look at that above his head, there's, I don't know, more than 10 there. So 10 or more, we're going to pick this value here, 1.33. Okay. That's our G32 and our G31. And our strength sharing factor, you can graph it if you want. But let's come back to, instead, go to this equation. K9. All right, we have our G31, which was 1. We have our G32, which is 1.33. So it's 1 plus 1.33 minus 1 multiplied by 1 minus, and now we've got to find our S and L. So S is the center-to-center spacing of the discrete parallel members, and the L is the effective span of the parallel members. So let's take the example above your scene's head again. The spacing between them looks to me to be about 100 millimeters, maybe 150 mil. And I don't know, what's the span of those beams above your scene?
I don't know. Like,
is that a bed?
Same size. Yeah, it's a bed.
Okay, so 1200 span, probably 1.2 meters wide. Okay, so the L is 1200. The S is either 100 or 150, something like that. And so you work out that equation, you will get a value for K9. All right. Yeah. And the K9 value, what's the range of K9 values? K9 is not less than 1. Okay. So if you do this equation and you get a value that's less than 1, you just take it as 1. All right. So just to summarize, the K9 value, where you've got 1 beam on its own, your K9 value is 1. Okay. Where you're nailing some together and having them in a parallel system, it's only going to get better. So if you have a parallel system or beams nailed together, your K9 value is going to be greater than 1. Okay. So the conservative option is the one. All right, you guys get that, or do you want to ask more questions on it?
It says in the topic that there's a maximum that you can get for that value. Is that?
There probably is. What is that maximum?
From memory, it was 1.33, was it?
Yeah, I think it is. That's probably reflected in this graph. Strength sharing factor for K9. That graph is almost indeterminable what that means. Yep. Look, from memory, I can't remember what the maximum value is, but 1.33 does sound right. And it does sound plausible because we're saying how much extra capacity can you assign to these beams just because you have lots of them? And 33% sounds like a plausible number. Okay. So again, what this is saying is timber beams are a natural material. You're going to have one timber beam which is a bit under strength just because it's got knots in it, or it's got natural variations in it. But if you nail that to some others, you get to average that with the others. And so instead of having to take a really conservative value because we've just got one piece of timber, you get to take a better value, up to 1.33 more. Does that make sense?
Yep.
Yep.
You guys don't sound convinced. Are you sure?
That's good.
So
That gives it roundness to the topic. Just you describing it like that, I think it's good.
Yeah, okay. All right. Are you ready for K12?
Yep.
All right. K12's a pain in the rear as well.
Sorry, I was muted. So it said somewhere that glulam and laminated timbers are always one. Is that right?
Yes. Can you tell me why that is, or do you want me to tell you why that is?
Was it something about that they're much less likely to have localized defects?
Glulam and LVLs are already made up of a bunch of different laminates stuck together. So they've already got all the averaging you can imagine. Because I haven't got a piece, but next time you're in the structures lab, there's a piece of LVL in there. And I'll show it to you, and it's about 20 laminates all glued together. And so you think of it like this, it's 20 beams stuck together. And so because we've already got 20 of them stuck together, they've already built K9 into the member, I guess, would be the way of saying it.
What if you put two of those together and have 40?
Yeah, well, that's all very nice, but there comes a limit of diminishing returns. So they're saying no.
Okay.
We've already got all the benefits we can get for you.
So it wouldn't end up going up to the maximum of 1.33?
No, because they've already built the K9 into it when they give you the strength.
Okay. Yeah, fair enough.
Yeah. So you're right. For glulam and LVL, K9, sorry, is always one.
So if you double it, you don't get any added benefits.
Correct.
Just more weight.
Yep.
Okay, fair enough.
I mean, you get double the strength because you've got two beams.
Yeah, yeah.
But if you're using natural
rise.
timber, you'd get double the strength plus the 14%.
Yes. Okay.
Yep. So that is like when you come to LVLs and glulams, the strengths are higher than the timbers they're made out of because of that averaging, because of this K9 effect. So, I mean, if I can labor the point a bit, when you have one piece of timber like this, if you have a knot, then the knot goes all the way through the whole member. In an LVL, when they put the laminates together, sure, there's a knot there, but it's only in one of the 20 laminates. So it's only 1/20th of the way through. So you've got 19 pieces with high strength there. All right, all good on K9?
Yep.
All right, K12 is, if you've done any steel beams, you'll know about lateral torsional buckling, but K12 is basically saying that when you load up, if you have a tall, skinny beam, when you load it, it's going to flop sideways, okay? That's what all this is about. So let me find what clauses we have to go here. Table 3.1. Yep, here we go. Okay, table 3.1 is... Oh, that's a seasonal constant. All right. So if we have a beam out on its own and it's holding a load, if it's tall and skinny and quite long span, it can flop sideways, okay? This is a really big deal in steel design because steel design beams are really tall and skinny in comparison. Timber beams tend to be a bit chunkier and blockier, so this isn't as much of a problem, but it's enough of a problem that we have to factor for it. So, hey, I wonder if I can do this. Did that work, guys? Can you see that sheet I got now?
Yep.
All right.
Yep.
So here's the K12 factor. We've got 3 conditions. If rho b times s is less than 10, then our K12 is 1. That's all good. That's the best condition because K12 is only 1 or less. That means if our beam is stocky, if it's not very long span, the simple case, our rho s is going to be less than 10. K12 is 1. So let's look at the rho s. Rho b first is from table 3.1. So I come to table 3.1, and this is based on the strength. So there's our grades of timber. There's our rho b, whether it's seasoned or unseasoned. So that varies from 0.8 up to 1.2. Machine graded pine is always considered seasoned. So you get these values 0.75 to 0.91. LVLs, if you go to the chapter on LVL and glulam, you'll probably find these values are there. Okay. The reason is LVL and glulam are fairly recent products, recent innovations. And so when they're incorporated into the standard, they threw everything for them into their own appendix. Okay. Page 34, let's go looking for it. Appendix E. I'm not even sure what appendix we're looking for, but it's somewhere here. Oh yeah, chance, there you go. Section 7 is glue laminated construction. And if we look down here, there are your properties. There's the rho B for beams. This is the same factor. So depending on your grade of glue lam and your ratio of temporary design effects, it's a bit more complicated, but there it is there.
So
Right,
which one do we use, the R1 value or the R0 value for that table?
In glulam?
Yeah.
Good question. Where were we? We were in chapter 7, that's right.
So they give us they've got those R values across the top, but we haven't looked into those yet, so we just don't know which one to use.
This is row B. You're talking about table 7.2?
Yep.
All right, this is the ratio of temporary design actions versus the total design action. So if you're only designing for permanent load, you use the ones in this column.
Yep.
If this beam has effectively no permanent load and it's all temporary load like wind, you're over in here. If you're halfway, it's here. So it's about the ratio of the dead load to the live load.
Yep.
Okay. All right, let's go back to our natural timbers. So we're over here. So we pick an example, F17 timber sees in 0.98, okay? So that's going to be this rho B value. Next thing is we have to find is S. And S is the slenderness coefficient, okay? Slenderness coefficient is really about the height of the beam versus how thin it is and the span. And so we've got a bunch of different conditions. So we have to look down these pictures down here and go, how is our beam supported? All right. If it's a beam in the air with just the loads on it, it's got virtually no support, then you're looking at this one here, except without those. So your LE, which is your L effective, is the same as the span. Okay. So you'd use condition 1, which is this equation. That is discrete lateral restraints to the compression edge. Okay. If you have, sorry, that's unrestrained. I wonder if I've made a mistake here. Hang on, just give me a second to review this. Continuous restraint. All right, well, I'll come back to this point about completely unrestrained, but you have restraints on a beam. So if you look at Yassine's head again, above his head, you can see that the layer above those timber beams, if you imagine that was a floor and they were floor joists, they effectively are attached to the beam, right? So they're attached to the top. If they're attached to the top and you've got gravity loading, then the compression edge is the one that's restrained. So that's situation one. This is the equation you use. S1 is 1.25 times the depth of the member times the dimension B. I'll tell you where BD is. There's the B, there's the D. Those are the dimensions of your beam, depth and breadth. All clear so far?
Yep.
All right. So there's our D, there's our B. Our LAY is the distance between those restraints. And there's a D there, and there's a power of 0.5. Now, actually, the more accurate situation is above Yassine's head there is those beams are continuously restrained along their compression edge. So there are nails in the beam, and if it's continually restrained, S1 is 0. Okay? If S1 is 0, let's quickly skip back up here. If S1 is 0, then rho S is less than 10, K12 is 1.0. Okay? That's the happy situation. You have fully restrained your beam. Okay? Let's say you fully restrained the tension side. So again, let's look at Yassine's bed there. Thank you for giving us an example, Yassine. Let's say that's got uplift load though. In uplift load, all those beams are restrained at the top, but that's the tension side being restrained, okay? And if you know about lateral torsion buckling, it's the compression that goes places. So restraint on the tension side is not as good. So your S1 is 2.25 times D over B, okay? And that S1 then goes back into this equation here. Multiply it by rho S and see if it's greater than 10 or between 10 and 20 or greater than 20. All right, now we've got, what if we have discrete lateral restraints to the compression edge, which means we've got a restraint, I don't know, maybe every meter apart or something. And there's an example of how it's built there. There's the equation. If you've got discrete lateral restraints to the tension edge, that's not as good, but it still works a bit. There's your value there. And lastly, number 5, you've got loaded on the tension edge with continuous restraint and discrete torsional restraints. So you've got this here and you've got little diagonals down there. That's a slightly more complex equation. Okay. How's that going for you guys?
So what's the deal with that? Because I think this is where we got it wrong yesterday when we were given the topic to go, that with number 1 and 2, if the restraints are close enough together such that that equation is greater than LAY on D.
Okay, if these restraints are really close together, then your LAY value is very small.
Yeah.
And consequently, your S value is going to be very small. If your S value is very small, you're going to get rho S as less than 10, and your K12 is 1.
Yeah.
All right. I wonder if I have a graph here. Here's a graph of the slenderness coefficient. So when your rho S is 0 to 10, there's your K12 value, it's 1.
Oh, we can't see the graph on our
Oh,
screen.
sorry. Yeah, sorry. This is the K12 factor here. When your rho S is between 0 and 10, which is basically means your beam is well restrained, all right? Then your K12 factor is 1. When it's between 10 and 20, between 10 and 20, then your K12 factor is going to vary from 1 down to 0.5, okay, in a straight line. And then, so that was the second condition. Third condition, if rho S is greater than 20, then K12 is, and there's an equation there. And basically you get this curved line here. What it's saying is as your beams get more and more slender, they get less and less efficient. So if your between 0 and 10, you're using the full strength of your beam. If you're down at 20, well, they're limiting you to half the strength of your beam, and below that, you're down to 20, 15% of the strength of your beam.
Yeah.
So the way you can increase the strength of the beam is not so much use a bigger beam, but just restrain the thing. All right?
Yeah.
Values down here are honestly pretty rare because they tend to be, the only way you can do that is to use these tall, slender beams and make them span a long way. So if you go into a house or a garage where you can look up and there's timber trusses at the top, you'll often see bracing between them, either just blocks of wood between them or sometimes cross bracing like this in older styles. That is all about getting this value here down. Okay, it's restraining the bottom of the beam and getting decent restraints on that. Okay, so the K12 factor, the maximum value is 1, and it can be a lot worse than that.
I think for myself, and I know we had a crack at this yesterday, trying to decipher which one to actually use, maybe.
Yeah.
So we had a beam. We both ended up with the beam that was 6. Was it 6 meters, Ian? And then it was restrained halfway. So our length would be 3 meters.
That's correct.
And I think, did we both have floorboards on them? I can't remember now.
Yeah,
I had one. Was it floorboard, like a plyboard floor?
Yeah, plyboard floor on top.
So which formula should we have gone with? Because it seems to be restrained with the floorboard going on top of a beam.
I went with 1.
There wouldn't be a wind resistance.
You should have gone with either. Okay, and the load is down, right?
Yeah.
Okay. Yeah. If the load is down, then you're talking about number 1 or number 3.
Yeah. Okay. Yeah.
If
we went with 1, didn't we, Ian?
Yeah, but we tried using that LAY on D to try and verify it first.
Yeah, that's right.
Probably where we went wrong.
Okay, so it's either 1 or 3. You talked about discrete restraints. Can you say the problem again?
So
I'll try and get it. I'll try and find it.
The beam itself's glue alarm. There's a beam on a roof span that's got a plyboard floor on top. The beam's 6 meters long with 1 discrete restraint in the middle.
Okay. If it's got a plywood floor on top and it's attached to the beam, then the discrete restraint in the middle is a distraction because it's continuously restrained. Okay. So I'll have to review the question just to make sure, but if it's got a plywood floor and it's attached to the beam, then it's this situation down, S1 equals 0. Okay?
Yeah.
Now, the only thing it's told me, though, that I'm worried about is the fact that you said it's a roof beam. And if it's a roof, sometimes you get uplift from the wind. If you've got uplift from the wind, what you've actually got then is situation 5 here, where you've got uplift on the tension edge, continuously restrained on the tension edge, and you got these discrete restraints here at, what did you say, 3 meters?
Yep.
So if that's the case and your load is uplift, then you're looking at this one. So S1 is 1.5 times the depth of the beam divided by the width of the beam. And over here you've got pi, and you've got D, which is again the depth of the beam. And you've got the space between those restraints, which I think you said was 3 meters. That's just 0.4. That's squared. That's the thing of 0.5, so you can work out the S1 value.
And with the 5 value, just sort of related to this, because if we're talking about the wind loads and stuff,
yes.
Say if we're given a question where the building is expected to see both updrafts, which are 5-second loads,
yep,
and snow loads, which are 5-month loads.
Yep.
Which 5 value would we use? Would we always use the greater?
Yep. Now you are talking about, you're mixing up 2 things here. The 5 value is the capacity factor. I think you're talking about K1.
Oh yeah, I'm talking about K1, sorry.
Yeah, no worries. Okay, let's just hold that thought for a second. Are we all good on K12? before we move to K1?
I think
I'd
so.
say a lot more of an understanding, yeah.
I think it's still going to be a bit tricky deciphering through the question and knowing exactly which one.
Yeah, if you can look for the question and pull it up and we'll do it together.
Oh, okay. Yep.
Yep. Have you got it there handy right now, or should I go to K1 first?
Jump to K1. I'll come back. I'll just grab this up. Sorry.
So Bryce's question is, you have a beam which has snow loads, which goes in certain regions goes for 5 months over the life of the structure. It also suffers wind loads, which is 5-second load. It's got a bit of dead load. What do you use for K1? And the answer is a little bit complicated, because what you have to do is you have to work out the worst case scenario. So you have to work out, if you had a snow load with a K1 value of 0.8, what's the limit of it? Yep. Versus the wind load with a K1 factor of 1, what's the limit of it? What I mean by that is you multiply the load, you divide the load by the K1 value and then have a look at it. So the K1 value for snow, for the strength of the timber, is 0.8. You take the snow load, you divide it by 0.8, so you exaggerate a little bit. That then gives you, basically, let's call it the equivalent of what it would be if it was a wind load. So you got the wind load divided by 1, which is just the wind load, the snow load divided by 0.8, the dead load divided by 0.57. Which of those gives you the worst load? And that's the K1 value you have to use then.
So you got to compare the load on top. So put each load on top of its retrospective K1 value, and the greatest one is the one that you use.
That's correct. Because if you think about it from a failure point of view, you've got this thing and you're trying to decide, is it going to fail when the snow is on it, or is it going to fail when the wind's on it? So you look at the snow load with its K1 value versus the wind load with its K1 value, which is more severe.
Yeah.
All right. Any chance you can find that problem?
Yep, I've got it. Would you like me to screen share?
Yeah, sure. Question 1, find the capacity of timber beam. The beam is a single, is there a diagram above that or not? No, okay, sorry. The beam is a single beam, so that takes care of your K9 value, all right?
Yep.
A single beam which spans 6 meters and is braced to compression edge at the ends and midspan only. Primary member of the commercial building. Okay, so can you guys look then at the table and which situation we're using?
Mm-hmm. We're using number 1, aren't we?
We are using number 1, yes, because I've said it's braced to the compression edge at the ends and midspan only. So if it spans, what was it span? If it spans 6 meters, can you stop screen sharing and then?
Yeah, I can stop.
Okay.
There we go.
I've stopped you. So back to here, I said what is it? Sorry, restrained.
Number 1.
Yes.
Yep.
Restrained at the compression edge, so it's either 1 or 3. And I said it's restrained at the compression edge at the ends and the midspan only. So your L effective then is half of what the span was, which was 6 meters. So half of that's 3 meters.
Yeah.
So it's whatever the dimensions of the beam were, the D over the B. The LAY is 3 meters. Do that in millimeters, 3,000.
Yeah.
Divided by D, you do that, you'll get a value of S1.
And D is our longest length, isn't it? So
no.
This, oh, it was the shortest one, was it?
D is that dimension there.
Oh, that's what I meant. Yeah, the longest.
Yep.
Because you got 100.
No. D is the vertical dimension. Okay. Have a look at your scene's bed again.
Yeah.
Where that beam is eventually effectively rotated 90 degrees. Okay. D is the depth of the beam. B is the breadth. Sometimes B can be greater than D. Most times when you put a beam in a structure, you put it upright like this, and so D is greater than B.
Okay, so you use the words wide and tall, so yes. D would be tall.
Correct.
Okay.
Yeah.
No worries.
Yes, so I did use wide and tall deliberately just to avoid that confusion.
Awesome. No worries.
Yes, it's the tallness, it's not the larger dimension.
Okay.
It might be the larger dimension, but not necessarily.
Yeah. Got it.
So in D is the largest dimension. For the Z value, we use the first equation.
Yes.
Yeah. Okay.
That's right. ZX is the business bending. So D squared. The tallness of the beam is the one that's squared. Okay. That's the primary bending. There's also bending in the other direction sometimes, which is the ZY value. It rarely comes into it. Okay, this is the main one here.
Yeah. I'll just make sure because we're having a bit of strife with that one as well. Which one to use exactly?
So
what were the dimensions of your beam again?
This one is 100 mil wide by 300 mil tall, and 6 meters long, but restrained halfway.
Okay, so let's do it if you like. And so our S1 is 1.25 times. Sorry, what was D?
300 mil.
300. And the B?
100 mil.
100. That's also then 300. And we decided LAY was 3,000.
Yep.
Okay. So that's 10 in there, square root of 10 times 300 divided by 100 and times 1.25. For S, I got 11.86. Is that what you guys got?
I'm still just typing away. A bit slower than you, sorry.
And what did you guys get for row B?
This is a glue alarm. Let me go have a look at the table.
Yep.
Sorry, my mic was muting and unmuting itself for some reason. I've found the table. Do we use stress grade GL18? Is that the one that says in the question, Bryce?
Yes, that's correct. GL18. And Peter, I got the same answer as you for S1.
Good. So what value did you use for row B? I'm going to try and position the circle over it.
GL18.
Yep.
What's it say in the question that the load it's going to go under?
Beam is a primary member. Commercial building structure. Mainly self-weight.
So it'd be permanent load?
Considered permanent, yep.
So it would be, we use the ratios.
You want to be using 0.82, that value there. Is that right?
Yeah, so the structure carries mainly self-weight, thus all load can be considered permanent.
Okay. So this one is 0.82. Therefore, your row S is 0.82 times 11.86, which is less than 10. Therefore, K12 is 1.
Awesome. And then if it's not, then we have to go through one of the other processes.
If K12 was 11, then you'd have to find what K12, sorry, if row S was 11, you have to find what K12 is by putting it into this equation here.
Yeah. And if it was more again, then we go.
And if it was more than 20, you'd put it into that equation there.
Yeah. Okay. Awesome. Thank you.
So I finally got a question here that specifies the moisture content.
Yep.
Because all the questions we've gotten so far doesn't. This one here says the timber type will be F8 seasoned and will be in a facility where the average moisture content will be below 15%.
Right.
Where do we go for that?
So if it was F8 seasoned, did you say?
Yep, F8 seasoned.
Okay. So the two things, the timber has been seasoned before it gets to site.
Yep.
And it's going to be an environment where the moisture content is less than 15%, where the humidity is less than 15%, which means it's going to stay seasoned.
Yeah.
Timber can unseason itself if it stays in a damp environment. Okay, but that's just saying use the values for seasoned timber.
So that would just be your one value for K4.
So K4, yeah. Let's have a look for K4. Just going to find it. There it is there. K4 is a partial seasoning factor. That's unseasoned timber. Seasoned timber. K4 equals, for seasoned timber, K4 generally equals 1. Okay? Where seasoned timber is subject to conditions where average moisture content is expected to exceed 15%, then you decrease K4. Okay? But in a question I said it's going to be in a drier environment, it's already seasoned. K4 therefore equals 1.
Yeah.
All right. Like I say, there's a lot of this topic is getting familiar with the standard that you flick to this point and then that point and this point and that point.
Yeah.
And that's hopefully, I mean, I made these tables to hopefully make that easier to send you to the right table or the clause, that kind of thing.
Might have a go at a question now.
All right.
See how I go. And then, so I think what we've done so far is timber properties.
Yep.
Then we did timber beams and compression. I don't know. Did you see and finish timber axially loaded beams? Did you do that one? You see? That's the one we did on Tuesday. I don't know if Yassine managed to finish it. He's muted.
No, I haven't.
Okay. Let's talk about that for a second, guys. First one is timber tension members is pretty straightforward. That's all easy.
Yep.
Okay. Timber compression members has also got a K12 value in it, but it's a different K12. Okay. You know how we had row B before? Now we've got row C here.
Is that
right there?
Just because of the compression?
Yes, because it's about compression. It's not about bending. It's a different, a different thing. That's why you have S values of S3 and S4. Okay, S1 and S2 are about the beams. S3, S4 about the columns. So it's a K12 factor, but don't get it mixed up because it's not the same K12 factor as the beam.
Yeah.
And what this is talking about is when you have a column which is rectangular, or I mean more specific, a column which is not square or circular, has different strength and bending in the weak axis versus the strong axis, right? If you look at this ruler, it's thick that way, it's really thin that way.
Yep.
When I bend it, it tends to buckle around the weak axis. Okay?
Yeah.
And it's possible to restrain the beam in the weak axis direction and not restrain it in the strong axis direction. So if I have this beam and I fully restrain it in the weak axis direction, then it's going to not buckle in the weak axis direction. It's actually going to buckle in the strong axis direction. That's why you have to consider here the minor axis, which is the weak axis, and the major axis, which is the strong axis. Sometimes you can pick it by looking at it. For example, if the column is unrestrained over its height, it's only going to buckle in the weak axis, so you don't have to bother with this major axis stuff. Just go straight to this one. Okay?
Yeah.
If it's fully restrained in the minor axis, then you don't have to bother with that. Just deal with the major axis. If it's like this diagram, it's weirdly done. You probably have to look at both.
Yeah.
Okay. But it's the same principle. You've got a row C value, and you've got a G13 and a G13 values, and it's basically about the length versus the dimensions.
Yeah. So when it's unrestrained, you can safely assume that it's going to bend around the minor axis.
If it's evenly restrained, it's definitely going to bend around the minor axis. Yeah.
Yeah.
Because the value B is smaller than the value D. Okay. So you look at S3 and S4, it's going to be, yeah, the smaller of that.
Yeah.
If you have a column which is completely restrained in one axis, then it's not going to buckle about that one axis. So you ignore that axis. So this is only for, you only have to consider them both when it can actually buckle around both axes.
Yeah.
All right.
And the effective length, that's generally just the distance between the supports, but then you have to times that effective length by the G13 value.
Yeah, you do. Let's have a look. Clause 3.3.2.2.
Because I remember Bryce was having a bit of strife trying to figure out which G13 value to use for each connection type.
All right. Columns, slenderness coefficient for lateral buckling under compression. Okay. Columns are rectangular cross section where you have a B, you got a B value and a D value. Okay. And you have to find G13 coefficient and get given in table 3.2. So come down to table 3.2. There's that diagram. And there's table 3.3. Where did 3.2 go? Here it is. Effective length for columns without intermediate lateral restraint. Okay. This is about the fact that if I restrain the ends of the column, it's not going to buckle as easily as if I let it rotate like that. You guys see that?
Yeah.
Okay. I restrain the ends of the column from rotation. It's less like, it takes more force to buckle it than if I just have it like that. Okay. If I have effectively a flagpole, okay, with load on it, and it can go sideways like that, it doesn't take much load to make that buckle. Okay. That's called a free top. All right.
Yep.
So these are the conditions. You'll find very similar conditions in the steel code as well. If your column has flat ends, that's an effectively a rotation restraint. So your G13 factor is 0.7. If it's restrained at both ends in position only, that was like my hands like this. My hands can't move sideways. It's restrained only, but not restrained from rotation. Then your G13 factor is 1.0. If it's restrained in one end in position and direction, but not restrained at the other in position or direction, then it's 2.0. What it's saying, that's the flagpole situation. We got this load on top, but it can go in any direction and rotate. Okay.
Yeah.
It effectively means sorry, go on.
I was just going to say, so is it the smaller the number, the more fixed it is?
Yes.
Yeah. Okay. Yeah.
Because when we come back to here, the slenderness is the effective length divided by that dimension of the column.
Yeah.
And so with a G13 factor, if the G13 factor is 2, it's basically saying it's twice as slender.
Yeah.
Okay? It's 0.7, it's making it less slender. So when you come back up here, is it less than 10 or not? You know, if your if your G13 value is 2, it's pretty hard to get that below 10.
Yeah. Okay. Cool.
And so with the 2 bolts on each end, it said it was substantially restrained.
Yes.
What about with the 4 bolts? Because I think you said something about that during your video.
There it is. Each end held by 2 bolts, substantially restrained, 0.75.
And what about when it's held in those 4 bolts in the square pattern on each end?
I think that's trying to say that it's 2 bolts in each direction, so it's substantially restrained in both axes.
So it doesn't change the number?
Look, when you restrain something by more bolts, it's going to make it more restrained.
Yeah.
So we'd use the 0.7 for that one?
I would have used 0.75. Held by 2 bolts, substantially restrained, 0.75.
And the same with the 4 bolts?
Yeah.
Oh, okay. Yeah. Even though it probably, as you said, it would be more restrained, but just use that factor.
Yep.
Okay.
And we only need to subtract the area of the bolts from the cross-sectional area in the tension questions.
In the tension questions, yes. So here's the tension questions.
I think you said that the bolts can take compression or transfer the compression, but in
compression, you don't normally worry about the bolt holes.
No, because they can take it or transfer it. Yeah.
I've said take note of empty bolt holes or other absent section. Often also compression, it's two things. It's about crushing the timber if it's really short, but in a longer thing, it's about buckling. The bolt holes are up here. They've got nothing to do with the buckling that's happening down here. So they're not really an issue. In tension, in tension, you've got to take out the bolt holes because it's area of timber missing from your section. So you take basically the minimum cross-sectional area in your member.
Yeah.
You'll find in timber design that tension is almost never a governing factor, tension of your timber, because it's really hard to design a joint to get enough tension into your timber member that it's going to break. It's normally about that joint's going to break first. And so if you have a tension, it's just easier to put a steel rod or something in like that rather than try and do it with timber. So tension's almost always about the connections. So you almost never use this equation here.
So it's more about finding the strength of the connection because the wood's always...
Yeah, when you come to the connections, you'll see that the connections often govern in timber design. Because you've got these forces in this timber and you've got to move it through bolts, and the bolts tend to rip out the sides and all that kind of thing.
Yeah. So like with tension, if you had two bolts in a row in the tension axis, only one of the bolts is going to be taking the majority of the load because it's the other bolt.
Oh, good question. So if you had, let's do on the other end here, if you had a bolt there and a bolt there like that.
Yep.
And you're taking tension load. Yeah, that's a lovely question. I'm glad you asked that, because the minimum cross-sectional area, you only have to take one bolt out of that, because that's the same cross-sectional area as, oops, sorry, I completely missed that line there.
Oh, right, because it's directly behind the other.
Yeah. So in fact, let me draw that second bolt in again. Okay. Assuming those bolt holes are the same diameter as on this side, it's going to break on the red line because you're missing more cross-sectional area there. It's not going to break on the blue line because you're only missing one bolt's worth of cross-sectional area, not two. So yeah, you'll come across that in the connections thing where you have to work out how many bolt holes there are in the cross-section.
So it only matters in the one plane, the amount that's missing.
Yeah, that's right.
Oh, yeah.
So I've actually said it here. In the example above, there are two holes in each row in the cross-section, thus n is 2, not 4. So that's when you're subtracting the number of bolt holes from the area. In this example, you're actually only subtracting 2 bolt holes, not 4.
Yeah. So that second column of bolt holes doesn't actually decrease the tension strength at all because it's in line with the other ones.
So if you want to get a lot of tension force into a member, the way you do it is you have a lot of bolt holes in a row like that. So you just, and you have a plate, that adds to that. So there's one member, there's the other member, and you've got, tension pulling them apart. With that number of bolts in a row like that, you've got a chance of getting all the force into the members. So yeah, but if you've only got a couple of bolts, it's not going to work.
Yeah.
Yep, because you only have to extract, well, in this case, if you don't have those 4, in this case, you'd only have to extract 1 bolt hole's worth from the area. So that becomes 1.
So it decreases. It doesn't make the limiting factor.
Yeah, that's right.
More.
You guys are good on that then?
Yep. And so bearing doesn't have anything to do with the removed areas. Is that right? Don't need to consider that.
Let me double check that for you. Bearing. I haven't got my bearing spreadsheet. No, my bearing diagram here. Not normally, no. I'd have to find my diagram, but not sure what that is. Do you want me to look into that? Or are you clear enough with that?
So as long as for now we're fine just using the Z equation. We don't need to worry anything about the bolt holes or anything.
For the beams?
Yeah.
No. For the beam, you don't worry about bolt holes because all the bending's really happening in the middle. You only worry about that when you come to connections.
Yeah.
So yes, that Z is just the pure section, BD squared on 6.
All right. And so all the information that we really need for the lab pre-work is going through these equations.
Yes. So in the lab, we're going to break a beam. So we're going to go through this equation here. The dimensions, because it's only one beam, K9 is 1. And because of the dimensions, I'll tell you for free that K12 is 1 as well.
Yeah.
All right. And it's really just about the duration of load. The K4, the timber's been sitting around in our storeroom long enough that we're going to call it seasoned.
Mm-hmm. Yeah.
And K6 is cold, so that's 1 as well. So that takes care of most of those factors. K1, of course, is 1 because it's a temporary load. Or it might be 0.97, I'm not sure, but I think. Where is it? 5 minutes. No, it's still 1. Yep.
Yep. So we've got to find the phi value, the force standard value.
So actually, now the phi value is a strength reduction factor, it's a capacity factor. And we're going to use, although this is the table here for that. So for MGP, you'd use structural members. Yeah, depending on whether it's a primary member or not, you'd use values ranging from 0.95 to 0.6. We're going to use 1 because we don't want any capacity reduction. We want to actually find out, we want to predict what the timber beam is going to do.
Yep.
So we're going to use 1 for that. And so it makes all the maths pretty easy.
Yep. So we're trying to find the unmodified strength value for the timber.
Yeah. So there's a difference between the unmodified strength value, which is predicting when it's going to break, versus the design strength. Because the design strength says we need a value that's safe enough to work, and so it doesn't fail. Predicting when it does fail is a slightly different calculation.
Yeah.
All right, and then for the compression one, again, we're going to use 1 for phi, 1 for K1, forgotten whatever the seizing value is for K4, K1 for K6. Again, we're doing a short column, so K12 is 1. So they're all 1s. It's really just the strength of the timber times the cross-sectional area.
Yep. And we're not doing any sort of bearing test, are we? Just the compression and tension.
We are doing one which is across the grain. So that's like a bearing failure kind of thing. So yeah, we will do that too.
Yeah. And since that's individual, we'd only use 1 for K9, and for K12, that would be substantially restrained because it's evenly spread across the top of the beam.
The only difference is the FC value. FC in compression, parallel to grain versus perpendicular to grain, they're different values.
Yeah.
And sometimes they don't give a value for perpendicular to grain. Yeah. I'll review that with you as well. So it sounds like you guys are ready to go, honestly.
Oh, what was the Z factor again? Sorry. What does that represent?
Yep, that's the bending strength.
Oh, that's right. Okay. Yeah, no worries. And then
so Z is BD squared on 6.
Yes, and that's the one we want to use. Does that for me? Yep. Okay. Awesome.
In case we don't meet up again before the next time, before we actually do the labs, are there any other topics you'd like us to do leading up to, say, the Charpy test or the concrete test or anything?
If you do concrete properties, that'll be good for the concrete. Sharpie, there's a materials properties if you want to get into it, but it doesn't matter if you do it before or after the lab.
Okay, cool.
Anything for the...
I shouldn't have recorded that because I might contradict myself to another group later on. Sorry?
Anything for the metal tension test?
Is there a material properties as well? That'll be good.
Yeah. So I've got that written down. So I think that's everything.
All right.
Excellent.
Well, Bryce, I'll hop into Discord and we'll finish up with that.
Yeah, that's awesome. Thanks for today, Peter. Really
no worries.